Okay. Does anyone know how to pin themselves? I'm not able to pin myself, so I'm not able to.
So I think you are already spotlighted.
No, but for me, I'm not spotlighted. I mean, on my screen, everyone's appearing, so I cannot make out what I'm showing. Oh. Well,
So you can do it in participant icon, I think,
participants.
and then searching for your name.
Yeah, on my name there is no pin. For everyone else there is a pin. It says pin for me, but for me it doesn't say pin for me. Anyway.
So it's highlighted already for everyone.
No, it's highlighted for everyone except me.
Oh.
So for me it's turning out as a very small window. Anyway. Okay, so I'm just gonna assume that, I mean, if there is something wrong, you'll just let me know. Okay, so in the last class, we had a look at using the transistor as a switch and operating a relay and how to connect a snubber diode so that everything, the back voltages are suppressed. So in today's class, we will start with what is known as an opto interrupter. So it's a very useful concept, and okay, if I write like this, it will be reversed. So I need to do this. I need to do this and this. So what we'll be doing is opto interrupter. Okay. So what's the deal? So in the last class, we saw that if you want to achieve some kind of switching, you sort of have the base of a transistor like this. So in this case, it's an NPN transistor, and then you simply have to drive the base into saturation. Okay, this was the basic idea, and you can drive the base into saturation with the help of something which can source a very small amount of current as well. So something like an Arduino can also drive this requisite amount of current. So what an opto interrupter does, so if you look into what the actual name is, so it's opto meaning it's derived from optics, and interrupter meaning it can interrupt something depending on whether light is shining on it or not. So as a student, I mean as a school student, you might have encountered something which is known as an LDR. Has someone encountered an LDR?
Yes, sir. Light dependent.
So it's known as a light dependent resistor, right? And so an LDR is it can be called as a very primitive optical component, because depending on the intensity of light at a given wavelength, the resistance will change. But here we are not so much bothered with an LDR. What we want is proper switching. Okay, so what is used is an opto interrupter, and the basic structure of an opto interrupter looks something like this. So first I will draw what is known as an optocoupler. Optocoupler. So an optocoupler looks something like this. So you have basically an input LED, and you have a line like this. So it's like a transistor, but there is nothing connected to the base as such. Okay. So now you imagine if this LED turns on, then the base is driven by the light. Okay, you can imagine this functional diagram to be as if this base is driven by light. So when this turns on, it gives the required amount of current and it switches on the secondary side. If I want to call this the primary, if I want to call this the secondary, then I can imagine that when the primary turns on, the secondary will turn on. And this achieves very good isolation. So it's called an optocoupler because it's coupling the primary circuit with the secondary circuit. Okay. So there is no question of backfeed. So there is no way there will be this secondary side which is backfeeding into the primary side. So now in order to complete this circuit, what are the different things that we need? If someone asks that, okay, this is so typical optocoupler component name is PC817. A typical optocoupler is PC817. It was originally made by Sharp, the Japanese company. Sharp. It used to manufacture, or I think it still manufactures a bunch of
Sir, it
players.
still manufactures television
Yeah,
sets.
television sets.
Refrigerators also.
Yeah. So Sharp was the company which came up with such an optocoupler, and the name of the component is PC817. And you will find this PC817 in a vast range of ICs wherever you have low voltage switching to high voltage, high current side. And why is it preferred over a relay? Because it doesn't feed back to the primary. There is no way to couple the secondary to the primary. Only the primary is feeding to the secondary. While in a relay, you know that because of the sudden switching, it will also feed back and you can possibly damage the transistor. We've seen this in the last class. All right, so in order to complete this circuit, what you would need is to drive this LED. You need to somehow give some sort of a one must drive this LED by some means, and in order to drive an LED, we know that we need a resistor like this, and we give a voltage source like this. So we have a VCC, we have a current limiting resistor R going across this LED and finally to ground. Now, how would you find out what the current of this entire system is? So it's VCC is going to be VCC minus the forward drop of this particular light emitting diode. So VF of the diode. Okay. So this will be equal to the current passing through this primary line times the resistance R. All right. So this would give you what, rather if you divide everything by I, it would give you an estimate for R. And the data sheet will specify. So the data sheet for PC817, and we'll open it in a moment. So the data sheet for PC817 will specify exactly how much current you should pass to the primary without damaging the LED. And it will also hopefully give us the information about the forward voltage drop of the internal LED. And this entire thing is sort of sealed. So that PC817, I will show you in a minute. It's a sealed unit. It's a sealed sort of IC, and it has only 4 legs. Okay. So I'll quickly discuss.
Sir,
Yeah,
so what is VF in the formula?
it's the forward voltage drop of the diode.
Okay, sir.
So every diode has a forward voltage drop. Okay. Despite allowing current to pass in this direction, there will be a certain amount of voltage that will be dropped, and that is due to the junction, the PN junction. Okay.
It is at
And sir, here the
0.7.
current,
Pardon me.
I'm asking, is it a 0.7 volt drop there?
Yeah, but it's not universal. The 0.7 volt drop is not universal.
Okay,
That is
sir.
for a
sir,
1.7 and simple complex.
and here I is the current through diode.
Yes, it is the current through the diode, and consequently it is also the current through the resistor as well. Typically this must be kept something in the range of 10 milliamperes or even lower. So if the resistance is too high, all the voltage drop will occur across the resistance, and consequently there will be no voltage drop across the diode. So if you are not able to overcome the forward voltage drop of the diode, then the diode will not light up. In fact, the circuit will not get completed. Okay. So do you understand? If I choose this resistance to be very large, what will happen? All the voltage drop will be across this resistor. There will be hardly anything left to cross the barrier potential. Whereas if this resistance is too low, then what will happen? If the VCC is high, then there's a chance that the current I will be so large that it will damage the LED, thereby damaging the optocoupler. Okay, so let's go to the PC. Let's go to the PC and have a look at the data sheet. I think I lost connection for a while. Share this. Are you able to see the screen?
Yes, sir.
Yes, sir.
So this is called as it's also called as a photocoupler. Optocoupler, photocoupler, and it's available as a DIP package, so dual inline package. So let's see.
Hello, sir.
Yeah.
Sir, I had read that the optocouplers are used for isolation between HV side and LV side in an electric vehicle.
Yeah.
So how is the diode able to withstand such high voltages?
So the
Like
diode
it will
does
be
not have to withstand any voltage. Okay. The simple answer is the diode is not having to withstand anything. So the diode, okay, this is the light emitting diode. It only gets signals from the microcontroller, meaning it's going to have something which is low voltage, low ampere. All the switching that's going to go on is between the collector and emitter. Okay, between 4 and 3 is whatever is going to happen. So now you will say that, okay, whenever I'm driving higher voltages across 4 and 3, there's a chance that this collector emitter path can get damaged, right? The only thing that can get damaged is 4 to 3.
yes, sir.
But
Sir, but
so
this is a one-sided communication, right? Like I can communicate from the 1-2 side to the 4-3 side, but not.
yes, not the vice versa.
So what if I have to communicate from a high voltage side to a low voltage side?
No, so then you have to use the low. In high voltage side there is a ground line, so you have to put sense amplifiers in the ground line. You cannot use an optocoupler to do that task. There are other ways of doing it. And the whole point is to not allow 4-3 to communicate with 1-2. Okay? The whole point of this is not to allow the cross communication. Okay, so as I was saying, if we go to uh, the ratings, so the forward current maximum, so these are the absolute maximum ratings. So the forward current maximum rating is 50 milliampere. The reverse voltage that you can apply maximum is 6 volts. After 6 volts, it sort of uh, breaks. The LED will go kaput. At the output side, the collector emitter voltage, the maximum voltage you can apply is 80 volts. The collector current is 50 milliampere, and the power dissipation total is 150 plus 70 milliwatt. Okay, it can provide an isolation voltage of 5 kilovolts. All right, and it also, I mean, Sharp being the professional company, it also specifies at what temperature you should solder it, because if you, I mean, if you don't follow, I mean, you can put it in the ballpark figure, but if it's low, then it doesn't work. So forward voltage, typically the voltage drop is 1.2 volts. Okay, this is the at the input side. The forward voltage drop is typically 1.2 volt. All right. At 0.5 ampere, you will have a drop of 3 volts, but you should not operate at this limit. The reverse current for a diode is typically very less. Yeah.
Excuse me, sir, what exactly is difference between maximum current and peak forward current that was there in the above table?
So the peak forward current is, I mean, when you apply at the primary side for a very short time, it can sustain an ampere. Like with any diode, if you continuously give 1 ampere, it will get damaged. But for a very short duration, you can give a current of 1 ampere. Okay, and it has to be that pulse should be less than 100 microseconds. So if you apply 1 ampere through the primary side at 100 for 100 microseconds, it will not get damaged.
Okay, sir.
Yeah. So okay. So where was it? Yeah. So the reverse current is what happens when you apply a reverse voltage to the diode. That is, you operate the diode in a reverse bias condition, and you will imagine that there should be no current going through the diode to the primary, but actually there is a leakage current of 10 microampere. Okay. So dark current for a voltage of 50 volts is 100 nanoampere. So what does this 100 nanoampere mean? That the primary side is off. Okay, it means that the primary side has not been energized. The the primary is off. Even if you apply an 80 volts or whatever volt difference between points 4 and 3, that's known as the dark leakage current, and that is approximately at 50 volts, it will give you 100 nanoamperes. So you would imagine that even when you apply a voltage across terminals 3 and 4, even when there is no primary side connection, you would imagine that it would stay off, but in reality it would have a leakage current of 100 nanoamperes. Alright, the breakdown voltages are also given that at 80 volts, the secondary side would break down. Okay.
Sir, excuse me.
Yeah.
So this collector door current is in the output side or in the input side, sir?
It's in the output side. Look.
Okay.
Okay. So for
Yes.
now, you don't need to really worry about all this. I've told you all the useful information. So let me see how I can do this. Mm, okay, let me know if my screen is visible.
Yes, sir, it's visible.
Right. So now the question that should come to your mind is, I mean, I've just told you that 50 volts and the maximum output current is not a lot. We saw that it was collector current is something like 30 milliamperes. Okay, and I'm just seeing this from the data sheet that the collector current at 5 volts is 30 milliamperes. Okay, so you have the and so this can carry a maximum of 30 milliamperes, and often for actuating relays this is more than sufficient. Okay, this is the relay side. Okay, so this is the relay. So even if you use a microcontroller, say 5 volts using an Arduino or whatever, so when this relay does the I mean, when you're actuating the relay, when it switches off, there is no way for the over voltage to go back to the Arduino. Thereby you protect the Arduino and everything else. Okay, this can be a typical circuit, or a typical circuit. So say this relay is a very heavy duty relay, and this relay requires maybe 100 milliamperes to stay on, so that the holding current, suppose that the holding current in under question is 100 milliamperes. Say it's a relay for a big CNC lathe. Okay, so say it's a holding current for maybe a CNC spindle. This could be very well the holding current. Then how do you deal with it? Obviously the primary can give you only 30 milliamperes. Then what do you do? Anyone who wants to take a guess?
So we can use a transformer.
Well, a transformer can be used if the signals are AC. They cannot be used with DC.
So amplifier.
Well, you can use a power amplifier, but in the last class, what kind of amplifier have we seen? I mean, we have not. I mean, I have shown it, but we have driven that into saturation. So
So that voltage reducer.
no. What you can do is something like this. So you have the primary going to ground, and so the output of this you can feed into the base of another transistor. And from here on, so you can make sure that this transistor can sustain a current of, so if the demand is 100 milliampere, you should see to it that it can sustain maybe 150 milliamperes. Something like a 2N3055. Okay, does that make sense to you? Then you have the same usual connection. You have the same usual relay connections to ground. Okay.
So here we are simply using transistor as an amplifier, right?
No, we have not used it as an amplifier. We have done the following. We have used a photocoupler to drive the base. So when the Arduino signal is high, then this LED will shine onto this hidden base. So this is not exposed to you. When this is exposed, this switches on with some nominal voltage drop across the collector emitter. So you essentially drive the base of a larger transistor via this resistor. Okay.
So, but
Yes,
like
sir.
in the main optocoupler, if there isn't any physical connection between the input LED and output transistor, then how does it switch on the base?
So that's the, I mean, this LED has a certain wavelength. It's in the IR wavelength. Okay, and I'll show you the complementary device also, so it will be clearer. So when it shines light on this base, the junctions are such that when you shine a light of a certain wavelength, it sort of causes the depletion region to become thinner. So all this boils down to the physics of the junctions. Okay.
Okay, sir.
So for the purpose of this course, it is not very important to know how exactly this works. But when this shines light, it causes the collector emitter to become conducting. Okay. And yeah, so let me just look up the properties of a 2N3055. I just told it as almost like a, I mean, if I remember correctly, but let us see 2N3055. So 2N3055 is a power transistor, meaning it should be able to drive larger currents. So let's see. So the base current is 7 amps. Oh, the base current is 7 amps DC. That's a lot of amperes. So let's go to saturation.
Sir, what is the nomenclature of these names? Like, how are they kept?
Not sure. I'm not sure. Okay. I mean, it's called as 2N or MJ2955. So I'm not entirely sure how they come up with the names. But you know, when you start working on analog electronics for a long enough time, you sort of start remembering things. Okay. So you see that the collector current can go into several amperes. You see? And the VCE drop is 10 volts. So for a V collector emitter drop of 10 volts, you can have this curve. So along this curve, you can obtain very high amperes, like 5 amperes, 10, and you can go all the way to 10 amperes as well. Okay. So a 2N3055 is a power transistor and it can get the job done. And it looks fantastic. I mean, it looks, I might have one lying around. Let me just check my box. I will show it to you. I will show it how, I will show you how it looks like. It's very common in all kinds of SMPS and all this. You will see, or power supplies, you will see a lot of such kinds of components. So it's 2N3773 that I have, but yeah, I mean, it's close enough. It does look like that. So can you see this?
Yes, sir, it's visible, but
So
some out of
you will,
focus.
yeah, it's out of focus. So you will see that it has only two legs. You will say that, okay, this has only two legs. You see, it has only two legs. But the third component is the body itself. So the body itself is the, so the body itself is the base pin. Okay. Otherwise, it only has two legs. Okay. So this is how these metal big transistors look like, and typically because they are sinking such a large amount of current, you must provide a heat sink for it. Otherwise, it will burn out. Okay. So yeah. So without leaving the computer, let me also show you the next item in our list. So today's lecture will split it up into two halves like we did in the previous as well. So the first one we will discuss about the optocouplers and opto interrupters. while in the second part we will discuss about 555. So the next component that I want to discuss is the Opto Interrupter, and the most famous one is the TCST 21. What is it? 21 TCST 2103. So let me share my entire screen. Let me know if the screen is visible.
Yes, sir.
So the
Yes, sir,
TCST
it's-
2103 is an opto interrupter made by Vishay Semiconductors. So the previous one was made by Sharp, and this one is made by Vishay, and Vishay is a very big company. So if you look at the diagram, so let's see what it consists of. It consists of a plastic base in which you have two limbs. The first limb is this one, where it's mentioned TCST 2103, that is the component name. And the second limb, it has written V19548. I don't know what this number specifies, but it helps in distinguishing the two legs. And let me just show you another image of it. Yeah, this image is good. So if you look carefully on this V69435, there is a plus and an E, and on the other leg there is a D and a plus. Are you able to see it in this image?
Yes, sir.
So I'm showing it through this because there is no way the camera is going to resolve this small feature. I mean, it's there on the breadboard, but there is no way you will be able to see it. So there's a plus and an E, there's a D and a plus. So let me copy this and let me put it over here. Okay. 2103. Okay, so if we go to this, look at what it says. Between the plus E and plus D side, there's a gap. So this gap, you have to basically use this gap to expose or not expose the two limbs. And what is the internal consisting of? It consists of a photodiode side, and rather it consists of an LED side, and it consists of a photodiode side, or the same thing that we had seen in an optocoupler. Okay, so let me just grab this as well. It will be useful to discuss. Okay, so this is the plus, this is the E, this is the D, and this is the plus. So the plus and E, this is the photo or the LED side, and this is the conducting side, meaning this is the secondary side. So if you were to connect this to a voltage source and suppose you connect this to ground, so if you sort of imagine it to be the same working principle as the previous one, I mean it's the same working principle. So you take this as the output voltage. So when you are driving the plus E side with the help of a voltage source as shown, so you have a resistor. This resistor, once again, it's the current limiting resistor. It's the current limiting resistor. So on the primary side you have VCC R, then the LED going to ground. Whereas on the secondary side you have VCC, which is the collector, and this is the emitter. If you imagine this as an NPN transistor as a BJT, then you have the collector emitter line like this. So you have VCC acting over here and the emitter going like this. And at the moment you forget about the resistances in the secondary side. I will show them. I mean, I'll show them eventually. So this circuit will always be connected like this. So the primary will always stay on. The whole purpose is the primary always stays on. So when this gap is open, meaning there is nothing which is inserted into the gap, then what is happening? The LED is shining onto the photodiode, as a result of which it's completing the circuit on the secondary side. So in this particular case, what will be the output voltage? So let's write it down. Nothing in slot. So this plus D line is conducting. So what is V out? What will be V out equal to?
VCC minus VCE.
So it's going to be VCC minus VCE. All right. But when you sort of block this circuit, when you put a card or some kind of object into this slot, so some opaque object in slot, when you put something in this slot, then you are basically interrupting this line. Okay, you are fundamentally disrupting this line, and so this collector emitter line gets disconnected. In that case, what will be V out?
0 volts.
It will be grounded, meaning it will be at 0 volts. Is this much clear to everyone?
Yes, sir.
Wonderful. So any questions so far?
So, like how VCA is become equal to VCE?
How did VCC become equal to VCE?
So like we write now V out is equal to VCC minus VCE.
Yes.
So then V out equal to 0 volt. Then I'm not getting.
This one is the doubt.
Not second line. Like how V out equal to 0 volt.
This one.
Yes, sir.
Okay, let me draw a simplified diagram.
So I thought V out should be VCC.
No, if this gets disconnected, well, let me draw it. Let me draw an equivalent diagram. So you have VCC, then a switch, and this is going to resistor and ground, and you are measuring this voltage. Now tell me, when this switch is open, what will be the voltage?
So 0, sir.
So
Understood.
that's this is exactly what we've written.
Yes, I got it.
And when this switch switches on, so I can do that, can do very cheap animations over here. So when this switch is on, then this becomes VCC, and so this becomes VCC. And obviously there's a drop, there's a collector emitter drop over here, and so that drop gets subtracted from VCC. All right.
Yes, sir.
Now does it? Okay, good. All right. So let me open the switch again. I have very limited animation abilities in this. So yeah, let me just close my door because there is some fabrication going on. Okay. All right. So how do you then? I mean, what is the use of this? I mean, all this is fine, but what is the use of this? Can you imagine an application for this?
So to detect some movement of any particular object in any machine, that
So this can be used as a counter, like how many times the voltage was changed
Okay,
based on the.
good answer. Yeah, count it. I mean, both of your answers are correct. So as
Sir, if the gap was higher, we could also use it like in conveyor belts. Like if an object passes,
Mhm.
it would block the light, and that would record it as one pass and so on.
So as a matter of fact, you can actually cut this and you can move them significantly apart. Okay.
So laser sensors.
Pardon me.
Laser sensors.
Laser sensors, not so much. Not so much. So let me, I mean, as a task for this week, I mean, assigned in this week, you can submit it sometime later on as well. What you will do is, I mean, of course, I will write it down properly and send it to you. But now let us take the cross section of this device. I need to try it here. So let's take this cross section. Of course, you have the legs. Forget about the legs for now. And you have a disc. Okay, you have a disc. So the cross section, if you look at the disc from the side, it will look something like this. And this is the axle of the disc. And maybe this is connected with the help of a coupler to a motor. So there's a motor input. So this rotates. So this is just the coupler. So this is motor, and this is known as an encoder disc. And an encoder disc is a very, very, very important mechatronic component. You will find encoder discs in a lot of applications where you need accurate movement of a motor. So you will find it in DVD drives. You will find it in old computer mouse. You will find it. You will find a lot of these in printers. In fact, I have obtained a huge amount of optocouplers from printers. Each printer has at least 2 optocouplers. Okay. Then rather opto interrupters. Sorry. So you will find this in printers. You will find this in copier machines. You will find this in almost any mechanical instrument which needs accurate movement and precise stopping or starting of movements. All right. So if I look at the encoder disc from the front, the encoder disc would look something like this. There would be a big disc like this, and there would be a bunch of slots like this. Okay, on the periphery. I mean, I'm not drawing, I mean, of course, you can imagine the slots are not going to look like this. They're going to look very uniform in nature. Okay. So, and this is the center axis. So when this rotates, now if I let me draw the opto interrupter leg in blue. So this is the opto interrupter limb, and the other limb is on the other side of the disc. All right. So here what will happen is when the slot aligns itself with this line, when the slot aligns itself with this line, it's allowing the LED light to fall on the photodiodes. Okay. But when this disc rotates a bit, so let me see if I can make it rotate. So when it rotates like this, when it comes to this position, what's going on? Anyone?
It will block the light and
It will block the light. So now if you imagine this same circuit, let's imagine this exact same circuit, this one. If you imagine this circuit, if I am just monitoring the output voltage, what will I get? If I sort of try to plot it on a oscilloscope, so this is time, this is voltage, what will I get? I will get a bunch of pulses, isn't it?
Yes, sir.
And so how can I estimate the RPM of this motor? How can I estimate the RPM? I mean, it's very easy question.
So by
So
looking at the
based on
frequency
number
of the
of
pulses.
peaks and time.
Yeah. So you know the time division. So how many peaks are there per time division? So you, instead of taking only one peak, you can take like averages of 5 peaks. Yes.
Yes, sir.
All right. Good. So this would be one of your tasks. And now I will show you the actual circuit in action. Okay. So before I sit down again, any doubts?
So you had showed that we could use another transistor to increase the voltage. So, but like, so does the voltage also increase with the current?
No,
Because
no, no,
like
no.
the
You are
current is
using a different voltage source. You are using different voltage source. I'm using VCC and VDD over here. You can use the same voltage source, no problem. But so suppose this switching was to happen at 100 volt DC, because why not? Maybe you have a circuitry where you have mains, then I mean, and this you will find in many machines as well. So then you will have mains going into an SMPS 1. So this will SMPS will give you a 12 volt ground, but at the same time, it will parallelly go into another SMPS, which will give you 48 volts ground. So this 48 volts ground is for the motors and relays, while this 12 volt ground is for microcontrollers, power, and all this optocoupler business. You get the point, right? So this could
yes,
be
sir.
at a lower voltage, this could be at a higher voltage. You're not amplifying voltage, you're just amplifying power. So you are having basically low power line like this, low power, and you are switching a high power line. Okay. So this could be like 1 ampere, who knows, even larger. Does that make sense?
Sir, is there any limit to the RPM? Like, since if it is running at very fast RPM, we are
Huh.
finding.
No, so ideally, on the oscilloscope, you can go to like nanosecond time. No problem. You can go as fast as you want.
So there will not be any like delay or something
No.
in
It's an
receiving the.
analog. So it's an analog device. So you quickly get all the signals without any perceivable delay.
Okay.
And the second thing is, now it's a very good question what you asked. Why? Because now suppose someone says, okay, I want to actually show it on the screen. I want to show this frequency on screen. Then how do you go about it? You want to show that frequency on screen. So you being you say, I'll connect this V out to an analog input of a microcontroller. No? So the V out, this V out, you simply plug it in into an analog input of a microcontroller. And this would work. If you just graph the plot, the voltage, it would work. Yes, no doubt. But what would be now the limiting factor of this circuit, this microcontroller giving you the accurate RPM? What would be the limiting factor? What do you think?
So sampling time of like taking the input.
Good. And anything else apart from that?
The delay that the microcontroller creates.
So that's like the sampling time. What
Okay,
she
sir.
said.
So does the resolution of the ADC of the microcontroller that is attached to the digital analog
No,
signal?
here the resolution of the ADC will not matter at all. But you have also raised a very important point. I will come to that. But here, actually, ideally, it should not affect. But there is a point. So I will write down resolution of ADC. Actually, the next point is related somewhat to this. So just go a bit forward to this resolution stuff. So what is, I mean, apart from that, there is something else. You're ignoring something else. completely. Like the
Execution time
microcontroller
is
has to do a bit of calculation as well, right? It has to
yeah,
do,
execution time of that calculation
so
code.
there will be some execution time. There will be some execution lag. Fine. So now we will go back to his original answer of resolution of the ADC. I mean, I think you know the answer, but let us, I think you might have done it in DIY lab as well. How does the resolution of the ADC have anything to do with sampling time or the execution time? Well, the answer is pretty simple. If you are trying to capture the voltage with the help of a very large, like 12-bit or 14-bit ADC, if you're trying to capture data using this, it will take more time and it will take more clock cycles for the analog to digital converter to actually take the analog input to convert it into digital and feed it to the microcontroller logic. But if you were able to somehow reduce the resolution, if you were to reduce the resolution, the time required for the analog to digital converter would also reduce, thereby increasing your sampling time. Now the question is, do we really care about the resolution? And the answer is a big no, because resolution is as if you're trying to divide this V out into very small segments, very large number of segments. If you have a very high resolution ADC, essentially you are breaking it up, so each segment could be like 1 microvolt. But here we are going straight from 0 all the way to some VCC, something very close to VCC, actually VCC minus VCE as per the diagram. But this could be say 5 volts. So you are going straight from 0 volts to 5 volts. You don't care about the intermediate voltages. That is why the resolution of the ADC does not matter at all. Okay, in that case you can actually reduce the resolution of the ADC on the Arduino. You can actually do it for any microcontroller. So let me show it to you. Reduce the resolution of an ADC on Arduino. Okay, so there is something called as a read resolution, and so you can change the read resolution. You can, I mean, if this, there are easier ways of doing it. This is for the
Excuse me, sir. So, what exactly is the resolution? Is it like the accuracy?
yes. I mean, the resolution is, I mean, how small of a voltage you can resolve. I, I mean, I imagine you might have done it in DIY lab. So, say you have a voltage ramp like this. Okay, say you have a voltage ramp like this. This is time, this is volt, and if the resolution is very bad, if your microcontroller can only like read these discrete steps, so this is like a low resolution microcontroller. So if you give an analog input like this, the microcontroller will read something like this. You understand? It can only read these discrete levels.
Okay, sir.
So what was the resolution of the Arduino? It was a 10-bit ADC or what? 12-bit ADC? How much was it? Guys, you're not remembering DIY lab. This was there, I hope.
So we
Okay.
didn't. I
Huh?
mean, we didn't learn all these things in DIY. So, I mean, regarding resolution
Yes,
and bits, 10 bits, all those things.
You've become a robot. So your voice is coming very robotic. So let me tell you. So a 10-bit microcontroller has a 2 to the power 10, meaning 1024 level of resolution, and at 5 volts, if the resolution is 10 bit, then you get 5 divided by 1024 minus 1. So this is the minimum voltage you can measure. So it's 5 divided by 1023. So what is this? It's something very close to 5 millivolts. So if you use the default resolution of the Arduino, you will be able to read something which 7 millivolts. Arduino cannot measure 7 millivolts because Arduino can measure in steps of 5. It can go to, it can measure 5, it can measure 10, it can measure 15 and so on. So it will not be able to measure 7 millivolts. It will report it as 5. If it crosses 7.5, it will report it as 10. Whatever I said, does it make sense?
Yes, sir.
So we are not able to get the total thing, but okay. I mean, barely we are understanding something.
Oh, come on, man. This is okay. I'll send you some video links for this, but this should have been covered in DIY lab. Okay. I mean, this calculation, is it clear? I don't know. Anyway, I mean, okay, forget about whatever I said. Even if you don't understand analog to digital converters, it's not a big deal, but you can easily understand it. I'm sure everyone will be smart enough to understand. I'll send you the video link. You can have a look. So, any doubts so far? Forget about the ADC for now. Forget we ever discussed this resolution stuff. Sampling time and execution. Okay, this is important. If the code that you write, it's able to execute that calculation, that 5-point averaging or 10-point averaging very slowly, then obviously you cannot execute, you cannot find out the RPM. If the RPM is changing very quickly, you will not be able to find out the change in RPM. You will be only able to do it after it samples, after it calculates the RPM, it displays it on the screen, then it loops back and again samples, then executes the code, then displays it on the screen, again it loops back. So this is what's going to happen. Okay, so any other doubt before I go sit down and show you the actual circuit? No? Are we facing some network problem?
No,
No,
sir,
sir,
they are
you're
not.
clearly audible.
Because from my end it showed me just a few moments ago that due to bad quality something. So anyway, okay, if it's fine, it's fine. So let me again go back down and I will show you the Opto Interrupter. Okay. So just tell me this. So if I share the screen, will you be able to see the webcam or do I need to unshare the screen?
No, sir, we can see it. You can just.
Yes, sir, we can.
I think if you unshare, it'll be better because now the screen is
Yeah.
divided into two.
Okay, I'll unshare it.
Sir,
Unnecessarily.
but we can choose what we want to see. Like we can
Yeah,
focus
but
on
I'll
the.
not give you the choice. I'll give you no choice because someone may just keep seeing the screen and the demonstration will be lost. Okay. Okay. Well. So what do we have here? So the black part over here that you see over here, this is the TCST2103 and this side is the plus and E part and this side is the plus and D part. Okay, so on the plus and E part, the connections are for the LED, okay, the internal LED. So the internal LED side, just let me know if I'm outside the frame. No, I'm inside the frame. So the LED part between the plus and the E side only has a current limiting resistor. Are you able to see the current limiting resistor? This is the current limiting resistor.
Yes, sir.
Okay, while on the D and plus side, I have an LED. This is an LED, and this is the current limiting resistor for that LED. So basically, this LED is just to show that the secondary line is being connected or not. I mean, you could drive any other load, but here, I mean, it's easier for me to just use an LED to show you switching on and off. It's far easier. All right. So let me show you the values of the LEDs. So we have the multimeter again, I'll switch it on. I'll go to resistance mode. So this is the multimeter that I was speaking about. So it has a way of measuring capacitance. If you put the capacitor limbs between these two slots, across these two slots, and put the multimeter into capacitance, you will be able to get the capacitance, and you will be also able to get the HFE. You will be able to fetch the HFE, meaning the gain of a BJT of a transistor, and you just need to set it to NPN or PNP, and you need to put the emitter collector base into the appropriate slots. So if you see this, there's a bunch of slots over here, and you can measure that. So we don't want to do that right now. We just want to measure the resistance. So this is around 340 ohms. So let me draw it. So this is on the E plus side. Okay, so we have the plus, then the exact connections I'm showing. So this is around 350 ohm. It might be 330 ohm, that's a standard value. And on the secondary side, what I have done is I have connected an LED, and here I have connected a resistor. Actually, I have connected a resistor over here to the ground line, and here there is a LED. And I'm powering everything from 5 volts. I'm powering everything using 5 volts. So let's check out what this resistance is. Yeah, it's the same 330 ohm resistor. Are you able to see the multimeter value? No.
No, sir, it
No,
went
sir.
down.
Down. Okay, so that's also 330 ohms. Okay, so we have 330 ohms common. So let me make the connections. So the positive line is the green one, okay, and the negative line is the yellow one. All right. So here it is, and I will need something to interrupt. So we can use anything. We can use a piece of paper to do the interruption. So let me switch it on. I mean, let me. So you see the blue LED glowing?
Yes, sir.
So why is it glowing? Because there is nothing blocking the slot. There is nothing which is blocking the plus E side and the plus D side. If you take a look back at the schematic that we had drawn, there is nothing which is blocking this. The LED is able to shine on the photodiode and you get the current. Okay. So now let me use the pen to hopefully we will be able to block. So the pen, if will, I don't know whether you can see it.
So can you use paper?
Yeah, I'll use. Let me see if I have something smaller over here. Okay. So the paper is not entirely opaque. So you see it's still glowing. So let me find something. Okay, I have a card over here. This should be pretty much opaque. Okay. You see?
Yes, sir.
Yes, sir.
Sir, I have a question, sir.
Yeah.
So, like, we are carrying this experiment in a well-lit room.
Yeah.
Now, suppose you switch off the lights, but
Yes.
the light due to the LED is still falling on the on this like this thing. So,
Correct.
like, so it will form a infinite loop, and the LED won't switch off.
No, look at this. I don't know whether you're able to see properly. It's
No,
not
no, sir.
truly switching off.
Yeah,
It's
this is because like you are blocking the
ambient light.
light from the LED also.
No, there is no. This LED is on the other side. There is no way for it to reflect back. I mean, whatever will reflect through the card is going in. Okay. But each bounce, the intensity of light reduces. You have to also remember that. Okay, so you will go to an equilibrium. I understand what you're trying to ask. If I now, so the ambient light is also there, and whatever light is being reflected, but it's going to be very minimum. Huh? The ambient light is what is causing it to stay on very dimly. Okay, so if I were to, so there is, I mean, it's impossible for me to stick my thumb over here. So just have to take my word for it at the moment. Okay.
So is the light from the diode infrared?
The light from the photodiode is infrared, but the LED which I am using is a blue LED.
Okay, sir.
So as to minimize whatever crosstalk can happen. So, I mean, despite being blue, there will be some fraction of energy in the other spectrum as well. I mean, these are very cheap LEDs, and but the Vishay one is a expensive component. This one is the original Vishay TCST2103. I'm not using I'm not using what you say, a clone or something. There are many clones in the market. This one I actually got it from Germany where I was there. So don't worry about it being lit very dimly. Even if it is lit dimly, you can treat the, when it is dimmed, you should be able to treat it as a low voltage level, and when it is lit bright, you should be able to treat it as a high voltage level. So now let me show it to you on an oscilloscope. Let me try to show it to you on an oscilloscope. So for that I need to move my webcam upwards. Let me fetch. So we have the oscilloscope over here. So we'll only need one BNC for this. Okay, we've connected the oscilloscope. The probe multiplier is 1x, and so let me just switch it on. So we're gonna measure between ground and, so we're gonna measure the voltage across ground and the leg of the resistor. Okay, so channel 1 is on. So let me block light. So let me increase the volt. Okay, so now can you see the trace? I mean, are you able to see anything? Let me increase the
Yes,
brightness.
sir.
So the
Yeah,
trace you're
okay.
able to see. So now when I block the trace, low, high, low, high, low, high, low, high, low, high. Okay, fine.
Yes, sir.
Yes, sir.
Should I show it again? So you can find out the length of the object as well. If I tell you that this object is moving at a velocity of this, find out the length of the object. So how much time this stays on, right? How much time this stays off, then how much time it stays on. So you can easily figure out ways to find out the length of this object, the speed of the object. Okay. So I'm gonna switch this off. Anyone has any
So,
doubt? Yeah.
how can we detect speed, sir?
You figure it out. You figure it out. You can detect speed also. See, if you can detect RPM, you can also detect speed. Okay.
Sir,
So,
I think you
are you
did not take
talking
this.
in case of linear velocity or like
Yes, in case of
circuit?
linear also, you should be able to figure out the speed. So instead of rotary encoder, you will have a linear encoder. So instead of a disk with slots, you will have a strip with lines or rectangular slots. Okay.
Yes, sir. Got it, sir.
All right. So I'm
So
gonna
for
switch
that,
off.
we'll have to know the distance between the slots, right?
Yeah. So the encoder typically is well characterized.
Okay. So
So applications
So
of
here
this.
we have
Yeah.
in the oscilloscope we are measuring the voltage across the resistance, no?
Yes. It's the same circuit that I had drawn on the computer. It goes from high to low. You try to remember. Okay. You have the circuit in front of you. No. Right now the signal is high. Okay, I'm gonna show it again. Now it's gonna go low. Okay. Right now the signal is high. When there is nothing inside, the signal is high, and it goes low. So I can quickly share it. I can extend my arms and share the circuit again. Okay. So nothing in slot, V out is equal to VCC minus VCE. Something opaque in the slot, V out equal to 0. By 0, I mean something which is low, because ambient light and all is there. Is it clear? Whoever asked the question, I could not get who asked the question.
Yes, sir.
All right. So I'm gonna switch off the oscilloscope now, and we're gonna take a quick break, because I mean, if I take a continuous thing, the attention span drops. So we're gonna take a quick break, but don't go anywhere. There's a lot of fantastic things coming up, and yeah, we'll start with the 555 circuits. Oh, so okay, I'm gonna switch it off anyway. Before we take a break, what are the applications of this? I mean, the applications are immense. So let me go to the computer and show you some of the typical encoders, how they look like. And your assignments will be, I mean, you need to apply you need to rack your brain, because in many applications, multiple encoders are used. Okay, in many applications, multiple encoders are used. So I'm going to show you linear encoder in a printer. Okay, so there's a linear encoder strip in your inkjet printer, and it looks like this. Okay, the strip looks like this, but when you magnify it, it has a bunch of black lines. Are you able to see this image?
Yes, sir.
Yes, sir.
Yes,
And
sir.
and this is how the photo detector is there. It's there on the carriage. Okay. Usually the ribbon is over here. It's static, and the carriage, you know, it actually counts whether it's going left, right, whatever it's doing. It's able to count it very precisely. All right. So very useful item, super accurate, and the accuracy will be the gap between the two lines. So it can go down to like 20 micron, 30 micron accuracy. Okay, so let's see some rotary encoder. So what I spoke about can also be made like this. So you have a source and photodetector. Exactly what we have seen. You can also have an LED and what is known as a squaring circuit. But in this case, the TCST 2103, it doesn't require a squaring circuit. Okay. So now in order to find out the RPM, you need only one encoder. But in order to find out the direction in which the rotor is rotating, you need to use two encoders, and this will be a part of your home task to figure out how to use two encoders to figure out whether an object is rotating clockwise or an object is rotating counterclockwise. All right, and you will find lots of information on the internet, but before doing that, you try to rack your brain. All right, this can be used also for, I mean, something like this is present on a shaping machine. Everyone knows what a shaping machine is. This is called as a shaping machine. Okay, so on this shaping machine, there is a big vise. No, was it a shaping machine or? It was a grinding machine. Yeah, something like this. Actually, you know what? Let's go to YouTube and let's go to YouTube and I'll show it to you how it is important, how such a mechanism is important. Flat grinding. Okay, so you clamp a workpiece like this.
Sir, I guess audio is not there.
No, audio is not there. You don't need the audio right now. So the machine does these oscillations. No one has to really do anything once it's mounted. The machine does this oscillation. So how do you think would such an encoder help? This is automatic. Huh? This oscillation from left to right is automatic. So how do you think you can get it done with the help of this bad boy?
Like determining the position.
So you just need to figure out whether this stage has gone to a certain point. So you have a small flat piece sticking out and it goes into this slot, right? Is that what you meant?
So the table down is moving because of the rotation of some pulley systems below. So based on number of rotations.
Good guess. I mean, that could also work out. I'm not saying it's not going to work out, but this stage can have a small strip sticking out and it can go into the slot. This can go in slot. Yes?
Yes,
and
sir.
then it understands that, okay, it has come to the end point. You can use another strip on this side to tell the machine that, okay, I have now come to the other end. But connected to this, so this entire stage, like he just mentioned, is actually driven by a motor. So when the motor is rotating clockwise, this stage goes to the right. When this motor rotates counterclockwise, this stage goes to the left. So when this particular slot goes into this particular strip goes into the particular slot, then we know that the motor has to stop and the direction of the motor has to change. So you must now figure out a way of sensing from TCST 12103 and switching motor direction. Okay.
Sir, like, can't it be like there is some kind of reciprocating rack and pinion mechanism and the
No,
motor?
why that is not used is because sometimes you use a very small job on this. Okay. So typically what happens is, and I wish I could go to the workshop and show it to you, is this slot can be adjusted. There is a where is the mouse? Okay. Yes.
Oh, okay, sir, I understood.
So there is a big slot over here. So this slot can be moved in and out. Okay. That
Yes,
slot
sir.
can actually be moved in and out. So you can change the travel. So the travel is solely you can eyeball that stuff and you can change in how far or how in the slot is. So here it is in, maybe the slot can go all the way here. Maybe the slot can go all the way inside as well. As long as it goes into the sensor, the two sensors are telling you the end points of the stage. So the end points can be moved. Okay.
Okay, sir, thank you.
So you must figure out a way of reversing the direction of the motor by sensing from two such sensors. And this is exactly what is used in modern machines. This slot has been replaced by an inductive switch. So here's something for you to read about. It's called as a inductive switch. Okay, you can read about this in your free time. So let's take a 5 minutes break and don't go anywhere. I mean, you can get a cup of tea or whatever you like. I'm gonna turn off the recording. So disconnect, switch off recording.